And in the last lecture, we showed how can we solve an unconstrained optimization problem. And I also showed you through an example on the application techniques of control. And today I shall talk more about optimization problems, which is constraint optimization problems. And the constraint optimization problem should be started like this. The mathematical form should be something like this. So this is the standard form of constraint optimization problem. Let's try that again. Still no display. So let's start from the constraint problems. And in this section, we will talk about the feasibility problems first, and then I'll show by several examples how to solve special problems in constraint optimization problems. That is, the linear programming problems and quadratic programming problems. And finally, I shall demonstrate on how to solve ordinary nonlinear programming problems. And this is the mathematical form of a constraint optimization problem. And here, still we call this one as the objective function. Still the one to be optimized, we minimize. And this one are called the constraints, which means that the vector x must satisfy this constraint, and then I select what kind of value can make the objective function find its minimum value. So this is the physical meaning of constraint optimization problems. And also, this part, the constraint, can be composed of several constraints. So this one can be considered as a vector, a series of inequalities. And the solution of x satisfying this condition are called the feasible regions and the feasible solutions. And from the feasible solutions, we should find the x which satisfies, which makes the objective function the minimum value. Now let me demonstrate what kind of feasible region is for a special example. For this problem, we can see that this is the objective function which should be maximized, and we should multiply -1 to the objective function to make this one to change this one to min. And these are the constraints. For this example, we can select a certain region. For instance, x from -3 to 3 and y from -3 to 3, and we can select the square region and find the objective function value for all the points in this region. And this can be done using a command like this. We should use match grid and then calculate for each point within this area the value of the objective function, and then we can display it first. We try it first and then I should explain further about it. The first I will select x1, x2 for x and y. It is still x1 and x2 in the mathematical form. So we first should select x1, x2, and then we calculate the objective function for all the points within this region, and then we can display it using surf command to display the surface. And the surface is something like this. And it should be noted that not all the points on the surface are feasible solutions to the original problem because we didn't consider this part yet. So how can we consider this part? We can do it like this. For certain values, we can try to find whether for what kind of x1 and x2 values this inequality does not hold. So we can use a command like this to find all the points which does not satisfy this condition. This condition requires the sum of its two terms is smaller or equal to 9. So we should find all the terms which is larger than 9. Which means we have to find the terms which does not satisfy the first condition. And then we can set the value of Z for this point to NaN to exclude the points. And also we have to try to find the point which does not satisfy this inequality by introducing a command like this. And then we can also set the point, the objective function values for this point to NaN. I will explain that one later for you. And then we have the modified matrix Z. And then we can use surf command to draw the surface. The surface is something like this. So I'm using the NaN constant on purpose to exclude the points which does not satisfy the constraint. So in Matlab, if you are using plot or other graphic command, for values of NaN, the point will not be displayed. So this point will be excluded from the result. And we can rotate the area and observe the feasibility region. So for this part, we call all the points within this part the feasible solution to the original problem. And from the feasible points, we have to select a certain point which maximizes the original objective function. We cannot select other points in these areas. We can only select the points within the feasible region.